Today we're going to finish section 5.1. Remember the last class period last week and your web-assigned homework, which is due on Monday at midnight. In that work in 5.1, we approximated the area of the region. We approximated an area of a region between the graph of y equal f of x in the x-axis on some interval AB. That is between the vertical lines, x equal a and x equal b. So we were approximating an area. How did we do that? Well, we partitioned AB, the interval AB, into 4 or 6 or however many subintervals we were told. Then we picked a number in each subinterval and used f of that number as the height of the rectangle over that subinterval. Remember, we formed a rectangle over each subinterval, and we used either left-hand endpoints or right-hand endpoints or midpoints to find the height of each rectangle. You have to be told this. You have to be told if you should use left-hand endpoints or right-hand endpoints or midpoints. You get a different answer depending on which one you use, and but that's something in the problem. Remember, previously we just approximated area. And then what did we do? We formed a Riemann sum. Riemann is the name of the mathematician. A Riemann sum is just the areas of those rectangles. Well, today we're going to finish section 5.1, and we're going to find not the approximate area, we're going to find the exact area. And the process will be the same process we used before, only we're using n subintervals, not 4 or 6 or 8 or a specific number, and we're doing an extra step. We're doing step 4 here. We're taking the limit of our Riemann sum as n approaches infinity. That is, we're going to use infinitely many rectangles. Now, hopefully, in your last D2L lesson last week, you looked at that animation that I put in the assignment, because that shows you that the more rectangles you use, the better approximation of the area under the curve you'll get. Well, if you want to get exact area, you just use infinitely many rectangles. Okay? Now, this 4-step process for finding the exact area, understanding this process is very important for Calculus 2. Because in Calculus 2, the very first thing that's on the regular syllabus for Calculus 2 is to use this 4-step process to find, you'll do some more work with finding areas, but you'll move very quickly into finding volumes of solids of revolution or finding lengths of curves. Okay? And this 4-step process is just so important. Again, what's the process? You partition some closed interval, AB, into n equal subintervals. You pick a number in each subinterval, either left-hand endpoint, right-hand endpoint, midpoint, could actually be a random point. What do you do with that number? You put it into your function to get the height of the rectangle over that subinterval. You form a Riemann sum of the areas of these n rectangles, one rectangle per subinterval. And then you take the limit of this sum as n approaches infinity. In other words, you use infinitely many rectangles. Now, remember from the first of the semester, when we computed derivatives, we used the definition of the derivative, and it was a limit of a difference quotient? Well, remember, calculus is the method of calculation based on the concept of the limit. We're finding area under a curve, exact area. by taking the limit as n approaches infinity of the sum of n rectangles. So we're solving a very important problem, and we're doing it by taking a limit. First, we've got some preliminaries, though, to do. And the next thing we're going to do is a couple of preliminaries that'll make this problem of finding exact area so much easier.